In last video, we learned about the mechanics and the components of a convolutional neural networks. In this video, we're looking at some successful CNN's architectures. So here we go. CNN is everywhere these days. You can find CNN's application in many part of our lives, just as the application on image classification. For example, here, given an image, we'd be able to determine what is the most probable class belong to the image. And not only that, CNNs can also recognize similar classes. For example, if you have an image of a leopard here, not only CNNs know this is a leopard, it also have other classes that are very similar that related to that leopard. So such as a jaguar, cheetah, snow leopard, or even the Egyptian cat. So not only it picked the right class, it also know what is relevant to that class. You can see another example maybe here with the convertible, but it's also grill, pickup, beach wagon. So it's very, very powerful in that regard. You can use CNN to retrieve images. So given an image, you can find all of the related images. And this has been used in Google Images as well. You can use CNN to do object detection, detecting pedestrian, horses, dogs, cats, vehicles, and people on the boat. And this can be very useful in the application of self-driving car that I may use. Another really useful application is segmentation. So you can be able to segment out the object like a person from the road, from the trees, from the buildings, and so on. CNNs also apply into the arts, and this is a very powerful application called image style transfer. And so given an image and an artwork of some artist, maybe Starry Night or some very famous style, you can morph that image into the art style of a particular artist, famous artist in the past. And the result is very beautiful art-like image that reflect the actual image that we take. Well, I took the liberty to apply this art transfer to UVA Rotunda. And so if you have art something like this and apply to an image that we've taken from the Rotunda, we now have a very beautiful image, artistic expression of the Rotunda. And again, if you apply a different style, you now have a different image. Very nice painting. So a typical CNN architecture is quite simple. As you see before in the basic CNN architecture, what you do is you stack a few convolutional layers, followed by some ReLU, and then a Puli layer, and then put in another convolutional layer and ReLU and Puli layer, and so on and so forth. So your network will get deeper and smaller. And on top of the stack, we might put a few regular dense feed-forward networks, and finally a softmax layer. So many of the architecture we see will have followed this similar architecture. So first start with a first successful CNN's network called the LeNet 5. And this is based on a 1998 paper of Ian LeCun and other called Gradient-Based Learning Applied to Document Recognition. I would definitely recommend you read the paper. But the CNN architecture in the paper is described as follows. You started with an input image, size 32 and 32. These are all grayscale images, so only 2 dimensions here. And then you apply 6 different convolutional kernels. So you have a at the result, you have 828 and by 28 kernel, and there's 6 of these. So these kernels are, I think, 5 by 5. So at the result, your each feature map gets string from 32 by 28. Now, they didn't do padding at the time. That's why you see the image string a little bit. So you have 6 of these. And then you do some subsampling, very similar to pooling. So it reduced, I think these are 2 by 2. So it's reduced the size from 28 by 28 to 14 by 14, but you still have 6 feature map. After that, you do another convolution, and the kernel here are growing to 5 by 5. So your image shrunk from 14 by 14 to 10 by 10. But here you do a total of 16 kernels. So now you have a 16 feature maps. And from there, you do another subsampling or pooling layer, which reduce the size from 10 by 10 to 5 by 5. And then you apply a 1 by 1 convolution on these feature maps. So you apply 5 by 5 kernel on this feature map, and at the result, you only have a 1 numbers left, because when you apply 5 by 5 kernel on a 5 by 5 image, you put it on top of each other, you end up with a single number. But they do that for 120 different kernels, so you end up with a very dense 120 dimensions here, and then they connect it with another fully connected layer with 64 nodes, and finally the output with 10 nodes. The reason they have 10 nodes because you map it to 10 numbers. So these are really not letters here, but a number, right? Yeah, I don't know what to put letters there. It's supposed to be numbers. So output is 10. Okay. If you want to know a bit more details here, there's a table format of the figure I just described. Talk about all of these layers. You notice the map size keep increasing. What it means here is the network get deeper and deeper, not only into the depth of the network, but also onto the depth of the result feature maps, right? Feature getting thicker and thicker as the iteration goes on. The image size gets smaller and smaller. On the other hand, you start with 32 by 32 image. It gets shrunk to 28, to 14, to 10, to 5, and eventually to a single pixel. You notice that the activation function here is not ReLU. ReLU actually did not get invented until later on. So they use 10H instead, which is fine. It's just slower. And finally, they use the radio basic function, which is a Gaussian connection. You may have learned about this in SVM, but that's the activation they use. I have a demo here. See, I can show you on the LANAC 5 and how this apply to the letters. And this is actually used with the US Post Office services. So that was pretty cool. It was a tech letter, and even cooler, you can see it's invariant to the translation of the letter in the image. It's also invariant to scale, right? And this is show the powerful of the convolutional property that we learned from last videos. Do squeezing, you can change the width, the thickness of the letter is fine. So that was really interesting. And then from LANAC 5, they spawned a lot of different CNN's architecture that had been developed over the year that taken amazing advances to the field. And a good measure of this progress is the ImageNet large-scale visual recognition challenge, or is short for ImageNet challenge. And I think for the longest time, every researcher in the field was very excited about the ImageNet, and every year they submit their own CNN to this competition, and every year they announce a winner. So this become a really good benchmark for the computer vision community. So the ImageNet contain a huge number of images, 14.2 millions, and it started with a research group from Stanford, led by Fei-Fei Li, and she was just trying to build her own data set. And this become a more open source. Started with Stanford, but it's then become more open. So a lot of people start contribute to this ImageNet, and it's grow over 14 million image with over 1,000 different classes, and some of the classes really shuttle. So think about it like if you're trying to distinguish 120 or more different type of dog breed, right? So 1,000 classes. And because we have 1,000 classes, the benchmark would be based on top 5 errors rate instead of top 1 errors rate. So as long as the system return top 5 most confident classes, and it was one of them correct, then it would count as correct. All right, very cool. So here we're gonna look at the winners of the ImageNet challenge, And over the year, you can see the start from 2010 all the way to 2015 here shown. The first CNN's winner started in 2012 called AlexNet. We will talk about AlexNet. And then we'll talk about GoogleNet, which is the 2014 winner, and ResNet, which is the 2015 winner. And you notice here the trend is the errors rate is going down and going down fast with CNN's base method. Go down from 28% in 2010 all the way down to 3.5%. Top 5 errors rate. And you'll notice another trend here is that when you start the machine learning method have really shallow method. They don't have a lot of computational layers. But when you start with CNN, you start with 8 layer, and the winner have more and more layer at the time to go. ResNet have 152 layers, which is extremely deep network. Right? So we will talk about these 3 methods next. All right, let's start with AlexNet. Developed by Alex Gistevsky. Right? I think he was brilliant to AlexNet instead of his last name. And he's a graduate student from Geoffrey Hinton Group. You may notice Geoffrey Hinton here, one of the Turing Awards winner. And AlexNet achieved a 17 top 5 errors rate in ImageNet in 2012. It's much larger and deeper than the LeNet 5. And it's stacked convolutional layer directly on top of each other. So if you're looking to look into the architectures a little bit, you can see here is a bit more layers. Here it's stacked multiple convolutional on top of each other. And you may see some trend similar to the LeNet is that the feature map keep getting thicker, maybe into the end. And the image getting smaller and smaller and smaller until they flatten it out into 4,000 units here. Another thing you might notice is that the padding, you see this is have padding, so the image size they don't lose the strength based on image size. But you notice the use of ReLUs, right? And softmax at the end. So here's some innovation that AlexNet brought into the field. First use of ReLU. They use heavy data augmentation. We know what that is. It's part of the regularization for neural net. You drop out, which is another regularization technique that I mentioned before. BatSci, they use HGD momentum at the optimizer, right? Set at 0.9, and have some learning rate epsilon at 0.01 and reduced by a factor of 10 when the validation accuracy plateau. So they have a lot of configuration into the network to make sure it runs smoothly. This is part of the design of the network. The second network I want to mention today is the GoogleNet or GuleNet. If you want to go LeNet kind of terminology. So developed by Christian Strategy and others from Google research team. It is the winner of the Image Challenge in 2014 with below 7% top 5 errors rate. And it's 10 times fewer parameters than AlexNet. So it's a much, much lighter network. And it's much deeper than previous CNN's method as well. And the reason it can accomplish all of this, deeper and less parameters, is that it introduced the inception modules. Inception means a network within the network. And you might relate it to the movie Inceptions in 2010. Right? I think they may get the inspiration from the movie. That would be my guess, right? But here's the meme for Leonardo Inception moment at the Oscar. Now, Leo didn't get the Oscar for the movie Inception. He got it for something else later on. But he's kind of a fun jokes that he many times didn't get the Oscar, so he had to make sure he's not inside a Inception, right? A world within the world, right? Well, let's get back to the CNN's architectures here. All right, so Inception modules, right? So the way Inception module work is very clever. It is a network within a network. So if you think about it, you have a module, and within this module, it have its own network, right? So it's a sort of a local network topology. So if you treat this as a single module, inside of it you can design a network. So you can stack 3 different layers on here, and you have convolution, 3 convolution, and a pooling kind of process in parallels, and then concatenate them together at the end, depth-wise. Right. So you see multiple field size for convolution. So you have a 1x1 kernel, you have 3x3 kernel, and you also have 5x5 kernel. So what's happened is you look at this at a multi-scale. You detect multi-scale feature within these modules. You have a pooling layer as well to do some maybe average pooling or max pooling. And then you concatenate the output together depth-wise. So when you heard concatenating depth-wise, what does that mean? It means the output going to be very thick, right? Very thick at the end. And that may be a problem. So let's look into why is this a problem with the naive inception module computational complexity. So say you have an input of 28 by 28 by 256. This is maybe in some intermediate into your network when it's, the depth start growing. And you have different convolutions here with this number of kernels, right? And then at the result, you're going to have as many of that number of the depth, right? So 128 kernel, 128 depth, and so on and so forth. If you had to compute all of the floating points operation of these convolution, and you multiply all these numbers up, you end up with 854 million floating point operation. So this is very expensive to compute, and this is only a single module in the network, right? And even the pooling layer preserve feature depth, which means that the total depth after concatenation only grow after every layer. So you imagine you started 256, you done all this, you concatenate together, you end up with 672. A stack that deep. So it is not very sufficient nor sustainable if you have to go through multiple inception module. Your network may become so very thick. So somehow we have to think about a way to reduce the depth growing at every layer. And the way we're going to do this, we're going to have a 1x1 convolution, which is, I think, is a really interesting idea. So idea is if you have a input feature map like this, and you have a 1x1 convolution. So what happened? You think about 1x1 convolution, the future size gonna be kind of meet the 64. So you have 1x1 by 64. So think about it's like a little hole that dig through. If you lay it on top of this feature map, it's like a little hole go through all 64 depth, and at each slice of the depth, you calculate a dot product, right? So you have, you just having one single pixel go through of this and calculate all the corresponding dot product. So there'll be 64 element in that dot product, and then it end up with a single number on this output feature map, right? Now, the nice thing about this is if I do that for all of these pixel here, I end up with a single pixel thick of this feature map, right? And then I'll do that for how many times I want. So this is like if I want to do 32 filter, what happened is my output image is going to be 32, right? Because for each of the 1x1 convolution, I end up with a single pixel flat surface here. So 32 one be 32 pixel thick. So what does that mean? What it means here is I have successfully lowered the depth of the dimension of the input into some depth that I can control, right? I can specify how many filter I want, and it can reduce from the input depth into the one that I specify. So it's a very powerful technique. It preserves the spatial dimension because you see the 56 by 56 still remain, but it reduces the depth. So that's exactly what inception module we're using. It's 1x1 convolution, and they sandwich a one-by-one convolution with their other module, other operation in the inception module, and as the result, they was able to maintain the depth of the features depth in Yao, the output. So let's look into the computational complexity again, and you can see here with convolution, one-by-one convolution, even though it looked more like more modules here, the operation actually reduced by almost threefold, and it can reduce more if you choose to optimize it, design your module a little bit more prudently. So that's the way they overcome the complexity and overcome and then stabilize the network, right? And here's some configuration for GoogleNet. Certainly a lot deeper. It's 22 layers. Have many inception module together. So this module a lot more complicated than just regular convolution, right? This is network within the network. There is no fully connected layer except the output here. Lot less parameters. You notice when the network go deeper, it tend to have a bit less parameters. And, there is some many variant of GoogleNet proposed afterward called Inception v3, Inception v4. And it's also inspired the development of Exception, which in 2017. So GoogleNet is the basic for many other successful CNN architectures, but they based on a very similar idea. The third successful architecture I want to mention today is what called ResNet. ResNet developed by Kai-Ming He in 2015, and it is extremely deep. It is 152 layers, and it is the winner of the ImageNet Challenge with 3.6% top 5 errors. It took him from 2 to 3 weeks to train this network on a 8 GPU machine. So he's certainly wait around for a while before his network actually is done. Now the question that he posed though is, does more layer means better? And you would think you know his answer, right? Because he's a very deep network. But his experiment is that he have a 20-layer network compete against a 56-layer network at first in the experiment, and we run the training error and test error and so on, and end up to show that 56-layer perform worse than the 20-layer network. And what are the reason for this to happen? Is that caused because of overfitting, right? But the 56-layer network might have less parameters than the 20 layers. As you can see how GoogleNet have less parameters than AlexNet, even though they have more layers. Right? So no, it's not caused by overfitting, but it's just the optimization. A deeper network, it's just harder to optimize. Think about the gradient had to go through 56 layers. And you run into all kind of problem, including vanishing gradient, unstable gradient, and so on. It just, or make your gradient any meaning, right? So it's just harder to optimize with deeper network. So he proved that, okay, deeper network may not be better, right? However, he added something really interesting is that the deeper network should able to perform at least as well as the shadow one when you add a what called skip connection or a shortcut, right? So what you do is very simple actually. You take an identity function and you copy the solution from some lower layer and then map it identically forward. Bypass some convolutions in this case, right? So what happened is, in the case where you don't pass it, you are trying to learn some function h, right? You should go through it's a regular network. But if you pass it, what happened here, you end up with addition here, so you learn fx plus x here instead of h, right? Or you trying to learn fx, right? And fx is nothing but h of x minus x, right? And because it is h of x minus x rather than h, it's called residual learning, right? So this time the networks are forced to learn function f instead of function h. and it's based on the difference between the h and x, right? And the reason they do this is, for example, when this signal go through and its gradient becomes so weak that really doesn't make any change in the network, passing this forward might solve this problem, because now not only you go through the very complicated process of convolution, you also pass your signal forward, sort of like a shortcut. You pass your signal forward so it can maybe useful for the layer that later on, right? So how do you think about it? You can think about it, it's like bypass all the traffic here to get the signal go through bypass the traffic a little bit faster, right? So not only that, ResNet uses a lot of different configuration to make their networks efficient. They're the first network to use batch normalization, use He initialization that we learned before. They use momentum just like AlexNet. They use similar learning rate. Mini batch size grow to 256, but no dropout was used. And well, we won't have enough screen pixel here to show all 152 layers, but you can imagine they also have a bunch of convolutions here, right? And each of them may have a skip, so they'll pass signal forward instead of go through a convolution. The signal only also be passed skip forward, right? Just like that. Very cool. Okay, this figure just show how the regular DNNs versus the ResNet. And what regular DNNs, what happen is when you pass really deep signal to a deep network, at some point the signal just die out, and so all of these neurons that you see here make no difference to the parameters. So it's not really helpful. But if you have the same situation where the signal dying here, you still be able to take the identity function shortcut, go forward, so that the later on these layers still alive, right? They're still changing, not just dead here. So that was the intuition and the reason why this worked very well, right? Okay, you can see that happen here, shortcuts. Okay, so we're looking at this sort of an overall field, and you can graph different neural net and their performance, and this is your top ones here, so it's a little bit less than top 5, but it's still pretty good. Over the year, you can see these are growing more and more. And if you look at the top accuracy versus the number operation, just say how big, how complicated these networks are. A very interesting trend is that sometimes the network lighter and perform better than the heavier network, right? And the ResNet is very interesting because you can decide how many layers you want, and typically more layers give slightly better performance, but you also increase the network size and computation a lot more. And you see here this ResNet, different ResNet version. And you have Inception, you have GoogleNet here, and so on and so forth. Right, so that kind of give you a big appreciation of how much computation the network need versus how high performance it is. So in summaries, the fields are moving very rapidly, all sort of architecture popping out every year. If you follow some of these principles, you actually can write your own architectures. That's part of the interesting, exciting about the field. AlexNet, GoogleNet, and ResNet, and their variations are widely used in the field. A clear trend is that CNNs keep getting deeper and lighter and require less parameters. ResNet is both the simplest and the most powerful. And there is another interesting thing is 2016 ImageNet winner GBDNet. They just use an ensemble learning combination of different networks and to train to have less than 3% top 5 error. So that's ensemble learning still it works over there, right? So I hope through this lecture it gives you an appreciation of different architectures, and we will continue next time with more exciting networks architecture for you guys. See you next time.